debating whether to give the whole introduction as usual, but I decided I would. So, John graduated from Temple, PhD in 1993 in particle physics, and went to work at Rutgers for someone, I'm not sure who, and also doing high energy physics, and was there for a while, and then decided that he would go into cosmic ray physics, moved to Montana, and then came eventually to Utah in 2005, and he's been here for a while since then in a number of positions, and he's been, so at first he was just a visiting professor, then a research assistant professor, assistant research professor, which way are you supposed to say that? I don't ever remember, and was appointed as an associate professor last 2 years ago, in 2014, and now he's going to tell us about cosmic rays, telescope array.
Thank you, Doug. Is that for me or for? Okay. So this is, of course, a. How low do you want them? Does that work?
Yeah.
Okay. Okay, so this is, of course, a colloquium for a formal review. Now, this also happens to be the 6th colloquium I've given here since I arrived in 2005, starting with a tag team with Petra Huntemeyer on the flash experiment back in 2006. So yeah, I've been here about 10 years, and recently Telescope Array found out that we're going to be funded to expand the size of the array by a factor of 4, and the hope is that that will prolong the lifetime of the cosmic ray program here at least another 10 years into the future. So with that in mind, I thought that a good kind of theme for the telescope array portion of my talk would be in the form of a kind of a decadal survey, where I talk about where we were 10 years ago, where we are now, and where we're likely to be, or what we're likely to learn from the telescope array times 4 experiment in the next 10 years. Of course, you'll also want to hear about a couple of telescope array affiliated experiments that I've been involved in, namely the telescope array radar project, and most recently the lightning studies, which are the parenthetical other particles from the sky in the title of my talk. Okay, so of course I want to thank the members of the High Resolution Fly's Eye, or HiRes, and telescope array collaborations. There's a lot of overlap between these two, of course, but these are the people that I've been working with for the past, more than 10 years in some cases, and a lot of whose work I'm going to be showing here today. So when I gave my talk in 2007, I was talking about energy spectra, and I started out by showing this little video, which performs the spectrum shear transformation, converting the e to the minus 3 spectrum into a, let me go back and run that again. Okay, into a spectrum in which we can see the various bumps and wiggles. And
what do you mean by e to the minus 3 spectrum?
okay, so E is energy, and the gross structure of the cosmic ray energy spectrum follows a energy to the minus 3 fall off. Okay, but it extends over so many decades that without taking that energy to the cube out of the spectrum, it's hard to see a lot of the structure that's there. Okay, so that's what that movie was showing. Okay, and then here we see, this is actually a plot that I showed at the Colloquium in 2007. But I described cosmic ray physics as trying to understand the bumps and wiggles in this spectrum. The middle of the last decade was about the time that the Hess experiment observed gamma rays coming from supernova remnants, and this was widely seen as confirmation of the understanding of this part of the spectrum as being due to acceleration in supernova. There is a feature known as the knee, which is kind of a rigidity-dependent cutoff of the galactic component as lighter, starting with lighter and moving to heavier components drop out of the spectrum. There's a feature called the second knee, occurring at about 10 to the 17th or so. And then there was a feature known as the angle, kind of well documented, which we kind of understanding as arising from the E plus E minus pair production off of the cosmic microwave background. Now, the title of my colloquium in 2007 was The End of the Cosmic Ray Energy Spectrum. Okay, so this was big news at the time. Back in 1966, Grayson, Sept, Sapin, and Kuzmin postulated what's kind of now a classic comprehensive exam problem, which is that a proton colliding with the CMBR can produce a resonance, which will then disintegrate into a hadronic matter and a pion, losing energy in the process. And that places a distance scale on how far the highest energy cosmic rays can be coming from us, and also predicts the end, or at least a sharp turnover in the cosmic ray energy spectrum. Okay, so it was 66. This was predicted. About 40 years later, that the high-res stereo fluorescence detector, by measuring the energy by looking at light deposited in the atmosphere, was able to compile convincing evidence that indeed the spectrum did exhibit this break. Okay, and that's this break right here. That break occurs at a few times 10 to the 19th electron volts, 10 to the 19.75 or so, and that is understood as being the that's exactly where one would predict that cutoff should be from the GZK calculation. Okay, so fast forward to the Telescope Array Observatory. This combines a fluorescence detector, or actually 3 fluorescence detectors like the telescope, or like high-res, with a surface detector covering about 700 square kilometers. This is an array of scintillator detectors, a 1.2 kilometer grid. And since March of 2008, this detector has been collecting data on ultra-high energy cosmic rays in the West Utah desert. It's a hybrid experiment. So in addition to the fluorescence detector that high-res used, we've got a ground array, whereas the fluorescence detector determines the shower geometry, the geometry of the cosmic ray-induced air showers as they move through the atmosphere, okay, by determining a shower detector plane and then using timing information. The surface detector uses timing information about the particles arriving in the footprint of the shower on the desert floor. Information from the two of these can be combined in so-called hybrid mode. Ultimately, the fluorescence detector is used as a calorimetric energy measurement to set the scale of the surface detector energy measurement. The surface detector, because it can operate 24 hours a day, 7 days a week, not just with a 10% duty cycle, can thereby obtain really good statistics on the cosmic ray energy spectrum. Okay, so this is a picture of the cosmic ray energy spectra as measured by the telescope array. Dmitry Ivanov put this plot together. You can see there's various detector components contributing to this. Okay, at the high energy end and with the best statistics in black is the telescope array 7-year surface detector spectrum. Okay. There's also a monocular fluorescence spectrum in blue, and then spectra from Cherenkov and fluorescence light from something called the tail experiment. Okay, so tail is one of the recent telescope array upgrades. TAIL stands for the Telescope Array Low Energy Extension. And here's the Telescope Array Surface Detector. I'll talk about TA times 4 later. Okay, but this infill array, as well as the fluorescence detector pointing up higher to larger elevation angles, comprises the tail extension to telescope array. Okay. So, and that is what gives us information way down below 10 to the 16th in energy. Okay. So, in terms of what telescope array has achieved in the past in the past decade, is we now have a measurement of the cosmic ray energy spectrum, all of these bumps and wiggles, okay, over 4.7 orders of magnitude with a single detector. Okay. This is unprecedented.
So what is all that stuff on the left-hand side of the plot? What is that? It just looks like is that an energy? There's like a lot of units.
Okay, so it's the same. It's the same plot I showed before. It's energy cubed, okay, times the flux of particles, okay.
Oh, okay. So
Units, yeah, units, particles per square meter per steradian per second. Yes. So this axis is energy. This is flux times energy cubed to take out the overall e to the 3 spectrum. Okay. But yeah, this I think is an important achievement in studies of the highest energy cosmic rays made possible by the telescope array.
Error bar so big in that middle region?
These are all statistical error bars, so it's a matter of where different detectors have what are the apertures of the various detectors. We've got, so these black points here have relatively small error bars. Okay, so at 10 to the 18th, we're still getting plenty of events in our surface detector array. Okay, the tail data. This is coming from a fluorescence observatory. So 10% duty cycle, smaller aperture. We're just not getting as much statistics there. Combine them still to show that everything is consistent. All the spectra line up. Okay. Now, with this higher statistics in the energy spectrum, we can do detailed comparisons with the Auger Observatory in the southern hemisphere. Energy scales of the two experiments, there's some systematic differences that we're working on understanding. Okay, but by using the feature known as the ankle as a kind of a astrophysical energy calibrator, right? We can align the spectra and see that we get very good agreement up to about 10 to the 19.3 or so. Okay, so but above that, there's a difference between the TAST spectrum and the Auger spectrum. Okay, what's this due to? We got working groups trying to understand this. Is there some systematic effect in the detectors? Okay, or what would really be exciting is this some difference in the physics of cosmic rays in the northern and southern hemispheres. Okay, so with the improvement in statistics that we've gotten from telescope array, we're starting to be able to ask this type of question. Okay, does the energy spectrum depend on where in the sky we're looking? Okay. So this brings us to the topic of anisotropy. And this is what anisotropy was back in 2005. Basically, they're at the highest energy. There wasn't any. We just didn't have enough statistics. Okay, this is a plot of the high-res 1 monocular data set above some energy, maybe 4 times 10 to the 19th electron volts. You see we're limited by statistics, also by the kind of paramecium-shaped error ellipses, which came from the fact that we were reconstructing these events in monocular and had poor reconstruction in the shower detector plane. Okay, but as of 2005, there was really no persistent evidence for anisotropy in the cosmic ray sky. People look for things like global dipole enhancement, localized sources at lower energies where there was enough statistics to tell the difference. The Agasa experiment, a surface scintillator detector, thought it found evidence for some clusters, and this plot was actually made to compare the high-res observations with the clustering that Agasa had seen. Okay, but that signal didn't stand the test of time. Okay, so now moving ahead to 2015, after Telescope Array has been collecting data for 7 years, looking at energies above 57 eV. Everybody kind of look at this picture and squint for a second. Is everybody squinting? Okay. And there is a enhancement, should be apparent to the eye, in the vicinity of this X that's drawn here. Of course, squinting is no basis for a quantitative analysis of anisotropy. So what we wanted to do was perform a autocorrelation scan, basically counting the number of cosmic ray arrival directions within certain solid angles of one another. Okay, and indeed, at about an opening angle of 25 degrees, there is an excess of high significance. Okay, so this is something interesting. Okay, and it led to the publication of a paper, indications of intermediate scale anisotropy. This is an observation with 3.4 sigma significance. Was published in 2014. This then is another view of that data. Now I should say that the data from about here up is telescope array. The data in the southern half of the sky is from the Auger Observatory in Argentina. And in this picture, what we've done is taken 25-degree circles, superimposed them on top of each event, okay, and then let the color scale tell us about how many overlapping circles we have, okay, and the so-called TA hotspot stands out in that picture, as well as in the southern hemisphere. Perhaps there's a not quite as hot spot in the region of Centaurus. Okay.
What does the color signify? I mean, what's the difference between red and black?
Okay, so the color is a measure in some units of the significance of the excess. Okay, so if everything was the same color of blue, it would mean that we just have an isotropic distribution. Okay, the fact that I've got a lot of circles, 25-degree circles piling up on top of each other at this point, okay, is telling me that I've got an excess in that.
Don't distribution of points tell you about the anisotropy? I mean, you have points.
Yeah. So these, these are the same points, okay, but of course I started by saying everybody squint at this. Let's do something more quantitative than squint. Well, from here we get evidence that 25 degrees is an interesting angular separation. Okay, so let's take 25-degree circles, where does that 25 degrees from? Is it from, galactic and extragalactic magnetic fields smearing out arrival directions from a point source? We don't know. Okay, but adding together, stacking these 25-degree search circles on top of each other gives us a sense that there is a excess here above the anisotropic background. It's a way of visualizing. Okay, it's a way of visualizing the background. There's some number. There's some number I can associate with this. I can then ask, how often do I expect to see a fluctuation that big in an isotropic data set? Okay, and that's how I arrive at numbers like 3.4 sigma for the statistical significance of this result.
You had a question about what the black points are.
Okay, so the black points are galaxies within 45 megaparsecs of us. Okay, and the point is to show that while there may be some correlation with the large scale structure, it's not like a rock solid correlation. There are regions where there's a lot of galaxies fairly nearby where we don't see anything coming. The region of the Telescope Array Hotspot in Ursa Major, there are a couple nearby potential sources in there, but not an overwhelming number. So the hotspot in the south is towards the center. Yeah, yeah. But well, if it was in our galaxy, that we would expect a much stronger correlation with the arrival directions at these energies with particular sources in our galaxy. Also, you have to ask what in our galaxy can provide this kind of acceleration. We don't have an active galactic nucleus or something like that in our galaxy that's spitting out high energy particles that we know of.
That's not towards the center of the galaxy. The galactic plane is the U-shaped line.
So this is the supergalactic plane. This is the galactic plane. Yeah. Okay.
There's gamma ray radiated. We know that there's a gamma ray hotspot just above the galactic plane. That's from some unknown source. The Fermi bubbles, yeah.
The Fermi bubble, the energies associated with that are TeV kinds of, yeah. Okay. But yes, having anisotropies, having excesses, being able to do comparisons with structure is a big step forward. I mentioned the possibility of energy spectrum differences, comparing where we are comparing what we see with what is observed in the southern hemisphere. Something that's particularly exciting, if we look in this hotspot in the northern hemisphere, and the hotspot was discovered above some energy cutoff, but we extend the energy cutoff, look below that, and ask what we see in terms of an energy spectrum. Compare that with the energy spectrum we would expect in blue from the off hotspot cosmic ray sky. You see that there is, at the kind of edge of statistical significance, a difference here. Okay, in fact, the chance probability of these arriving from the same distribution is 6 times 10 to the minus 4. Okay, so this is significant local difference. If this persists, it would be very exciting news indeed. This is the kind of thing that we would like to see. Okay, so bring in TA times 4. TA times 4 will quadruple the surface detector aperture to about 3,000 square kilometers. We'll add 500 scintillation detectors on a 2-kilometer grid this time, okay, to cover more area. We're focused on the highest energies. 2 new fluorescence detector stations, one co-located with, well, actually both of them are co-located with existing TA fluorescence detector stations, but looking in opposite directions. Funding for the surface detector was approved last summer, and just this year we found out that the fluorescence detectors will be funded at the $1.8 million level. And Charlie Ray, John Matthews, and Gordon Thompson are the PIs on that grant. So the goal of the TA times 4 project is to increase our statistics to the equivalent of 19 years of TA surface detector data by 2020, and about 16 years worth of data in hybrid mode. And construction is underway on that project. And this is just the result of simulation, asking what, for example, the hotspot might look like after we've got 19 TA years worth of data. Okay, this is if the hotspot continues at the same relative level of intensity with respect to the background. Or what would be even more exciting than that, it would be if the hotspot has some substructure. Okay, if there's 2 or more sources within there, we'll be talking about statistics within the next 10 years where we can start to tease that out. Okay, so looking forward very much to the data that we get from that we get on that. Okay, composition is the third area of third major area of study of cosmic rays. Whereas we get the energy by looking at, in the fluorescence profile, how many particles are present at shower maximum, which translates to how many photons our fluorescence detector sees. One accesses the cross-section, the scattering cross-section, and hence the composition, okay, by looking at how deep in the atmosphere that occurs. Okay, if you think about it, a small particle, a proton, is going to be less likely to interact and therefore likely to penetrate deeper in the atmosphere than a big, large atomic nucleus like nickel or iron. Okay. As of 2005, this is what the data available to us on composition told us. Let me explain this plot here. So the vertical axis is the depth in the atmosphere, the mean depth in the atmosphere of shower maximum as a function of the log of the energy of the incoming particle. In blue, okay, are the predictions, according to some modelers, of what the depth of shower maximum should be for protons, how that should evolve with energy. Okay, and that's called an elongation rate plot. At the other extreme, we plot the elongation rate expected for iron. Okay, then keeping in mind that as you between the protons and iron, this is a log of the mean atomic mass mass scale for the primary. Okay, you can see that the observation by high-res circa 2005 indicated a primarily light, if not mostly proton composition. okay, above 10 to the 18th electron volts. Some model dependence, but that was basically the story. The systematic uncertainty reported in this paper, and I went back and read this the other day just to confirm that, was about 19 grams per centimeter squared. And that number should be compared with the 100 grams per centimeter squared difference between protons and iron in this plot. Now, I remember that number. Okay. Over the past, I'm not going to go through all of these in detail, okay, but over the past decade, there have been many experiments have taken cracks at measuring this depth of shower maximum versus energy. There's some extrema here. Early Auger measurements tend to indicate a very shallow distribution in the atmosphere. Perhaps the high-res data circa 2010 was the deepest. Okay, but taken together, these all are kind of starting to present a picture here. Okay, which is that more or less we have consistency emerging in terms of the depth of shower maximum. Certainly at energies around 10 to the 18th or so, it looks like we've got a large proton component, if not an exclusive proton component. Well, one thing I want to point out, though, is that the quoted systematic uncertainties in all of these measurements is about the same, okay, as the 19 grams that was quoted back in 2005. Okay, so while TA has gained statistics a little bit, or increased the statistics a little bit in this field, the systematic uncertainties, okay, which dominated in 2005, are still an important effect. Okay. And just turning up the increasing the statistics is not necessarily going to improve our knowledge of the composition. Okay, so we're doing other work in trying to understand the effects of cross sections and composition. My postdoc Rasha Abbasi did a calculation. Of course, if the depth of shower maximum depends on the cross section, then one should be able to infer the cross section from the depth of shower maximum, and Rasha was able to do that and produce a new number on the sigma pp, the proton-proton total cross section, okay, at an energy high above the LHC.
Is there some reason to believe it's either protons or iron? There's no calcium, no silicon, no.
Well, this is a. I could give a short answer to the question or a long answer to the question.
There must be a reason.
Well, I mean, so I would. So historically, I guess the reason is, protons are the lightest charged particle, so that has to be one rail. Okay, iron is the peak of the binding energy curve, so the elemental abundance drops way off after iron. Okay, so historically, that would be a reason why you might expect the mean X max to lie between the two of those. To the extent that your models, are accurate. Now, could there be other nuclei in there? Yeah. That's a long discussion. Maybe let's bring it up again in the question and answer. But yeah. Okay, so I wanted to show you Rasha's cross-section measurement. And then Rasha also has been looking with Gordon at how uncertainties in quantities that one can measure at LHC energies translate to uncertainties in predictions for the depth of shower max at ultra-high energy cosmic ray energies. So in addition to the cross-section, the fraction of collisions which are elastic, the charge particle multiplicity, all of these impact the depth of shower maximum that you would measure. Okay, and this curve is just showing how mean X max can fluctuate as a function of those. Focusing on the charge multiplicity, all the data we have on that, okay, is down here at center of mass energies 10 to the 3 GeV or so, okay, and there are models that describe that LHC data, or actually this is not LHC data. There are models that describe this data perfectly well, okay, but when extrapolated to the energies that we're interested in, translate to a big modeling difference, okay? And so the uncertainty in depth of shower maximum at 10 to the 19.5 electron volts, the GZK cutoff, where we're interested in looking, are of order 30 grams per centimeter squared, okay? Bigger than the experimental measurements, also bigger than the difference between the various predictions, okay? So to make progress in composition studies, okay, I think statistics is not going to be enough for us, okay? If I told you TA times 4 was going to solve all the problems, you wouldn't believe me anyway. So this is all. So I'll tell you, as far as composition goes, limited statistical improvement, but there are irreducible. There are experimental systematics. They're thus far irreducible at the 15 to 20 gram level, and theoretical model differences at the 30 gram level. Really progress in the composition studies is going to depend on these being resolved as well. Okay. On the other hand, energy spectrum and anisotropy studies, there's every reason to believe that we're going to learn a lot of exciting things with TA times 4, particularly as to this question of, is the energy spectrum dependent on where in the sky you're looking, and that's something exciting to look forward to in the next decade. Okay, so that kind of is the conclusion of my 10-year survey. Holy cow! And I'm going to have to get through some other stuff. Let me get a little shot of sugar here. Telescope Array Radar project. I've talked about that before. This was a project for which I was the spokesman, which was asking the question, can we use the radar signature of cosmic ray air showers to detect them as a remote sensing technique, and thereby improve the aperture so that we can get still more statistics at the highest energies. This is an old idea. This was first brought up in the 1940s, almost 80 years ago, to explain anomalies in atmospheric radar data. TARA is by far the most ambitious experiment ever to attempt to look for this effect. TARA is co-located with a state-of-the-art cosmic ray detector, has a several megawatt effective radiated power transmitter, which is broadcasting over the telescope array, and a fast receiver system. Okay, so the basic idea is we're transmitting across the telescope array surface detector. When a cosmic ray air shower is detected in the surface detector or by one of the fluorescence detectors, we look for a radar echo in the receiver. Provided the radar cross-section is large enough, what we expect to see is, because this is showers propagating at near the speed of light, is a highly Doppler shifted chirp here represented in a spectrogram frequency versus time space. Okay. The duration, though, very short, some tens of microseconds. Okay, so this is a picture of our transmitter, actually two television transmitters, analog channel 2, and this is our phased array of Yagi antennas, which brought that all that power in the forward direction. This is an image of our antenna pattern. Okay, and then this plot here is a plot of the received power as a function of frequency. Okay, of course, our carrier at 54.1 megahertz is standing out. Okay, but otherwise, our noise level is at the level of the noise level of the Milky Way galaxy. Okay, so we're operating this experiment in the best place in the Milky Way galaxy if we're hoping to be able to see radar echoes of cosmic rays. Okay. So what is hoped for? Okay, here's a simulated chirp and a simulated echo. Okay, this was for a particular air shower that we know passed through the field of view of Tara. Okay, however, we look at what was actually observed. We didn't see anything. Okay, and this was typical. And in fact, we got a number of air showers. You can see the green arrows here kind of indicate how the shower trajectory is oriented to pass through the Tara main lobe. And with these events, we were able to quantify what radar cross-section we would have been able to see. We placed 90% confidence level limits. We did it assuming that an air shower acted like a thin wire. That's a wire that's thin compared to a 6-meter sounding wavelength. And anyway, for the first time in 80 years of speculation, we were able to place at least limits on the radar cross-section. So as I said, by far this is the most ambitious effort ever undertaken to test this idea. And although we didn't see anything, we were able to place upper limits on this cross-section for the first time. A number of articles have been written and are being written. And it seems pretty definitive that radar is not going to be a practical remote sensing technique for studying high-energy cosmic rays.
I understand why it's not practical, but why aren't you seeing anything?
Why are we not seeing anything? The speculation would be that the degree of collisional damping, we don't have just free electrons in the vacuum, okay, that we're scattering off of, okay, but we've got free electrons that are colliding with neutral air molecules, and the rate at which that occurs, not well known. Okay, but one can infer that if it's high enough, the electron's tendency to do this will be randomized by the other collisions, and we won't be able to see it. That would be our guess as to why we're not able to see anything. Okay, which brings me to the other particles from the sky. One more shot of sugar and chocolate. Okay. The Telescope Array Lightning Mapping Array project. This is another affiliate experiment of Telescope Array, which I started and have been running. This was motivated when one of our colleagues in Japan, a postdoc by the name of Takeshi Okuda, noticed that in the first 5 years of telescope array data, we would get bursts of surface detector triggers. Sometimes, it's hard to see the scale here, but that's 10 microseconds. Okay, so bursts of surface detector triggers where there would be several surface detector triggers within 10 or 100 microsecond type time intervals. Now, given that the normal surface detector trigger rate is about 1 event per 2 minutes, okay, you can work out that these can't possibly be due to cosmic rays. Okay? Either something's going wacky with your detector, or this is some new phenomenon. Okay? And what we found was that all of these events, in fact, these events were a subset of events in which surface detector triggers were found to have arrive close in time with activity in the National Lightning Detection Network. Okay, so motivated by that, I read some papers and made some phone calls, and was fortunate enough to come in contact with Bill Rasan at New Mexico Tech. And his expertise is in forming three-dimensional maps of lightning strikes, okay, and GPS time three-dimensional maps, so that we can record the lightning information at the same time that we're recording the surface detector information. And we actually installed this back in 2013. This is Cosmic Ray postdoc Bill Hanlon here helping with the installation. We operated kind of unstably for a couple years before we kind of got everything squared away in October of 2015. Since then, we've been operating pretty stably, and we got some good news in April of this year. I was the PI on a grant from the NSF Division of Atmospheric and Geospace Sciences to study these events in some detail. And so we've got an array of these detectors that are scattered over the telescope array surface detector. How does a lightning mapping array work? Lightning produces impulsive radiation in the VHF. Here's an example pulse. Okay, you receive that with a receiver. In this case, it has a channel 3 filter. You have an array of these detectors, okay, each of which is measuring a time and an amplitude. Okay, you can fit that to find the x, y, z, and t of each of these impulses, and use it to form a three-dimensional image of a lightning strike. Okay, and this is a movie of a lightning strike that was captured above the telescope array surface detector. The color represents time. You can see this extends over several kilometers. In fact, we did not have any surface detector events in coincidence with this. I picked it because it was a pretty lightning strike. Okay. But what is it that we can see? What is it we hope to be able to see? So on the left is a movie that you can find on the web, and you can find lots of movies like this on the web. High speed video of lightning strikes. And what we see, I hope, is this visible here? Before the main lightning strike, okay, are these slow-moving lightning leaders. Okay, these move through the atmosphere at about 10 to the 5th meters per second, and they create a channel, a conductive channel, which then the main stroke, it's called a return stroke, okay, can travel, and that happens much faster. That's about 10 to the 8 meters per second, okay, or about a third of the speed of light. Okay, so these leaders are preceding the main flash. They're responsible for the current carrying channel, okay, and it is believed that it's the high fields in these leaders that are responsible for the phenomena of terrestrial gamma flashes. Okay, terrestrial gamma flashes were discovered aboard satellites in the early 1992. Originally, it was believed that they came from sprites. Now we know that they're due to intercloud discharges. Other experiments since then have improved statistics to the point where one can now make plots of the spectra of gamma rays that are arising from these terrestrial gamma flashes. Okay? And you see that the energies extend to 1 MeV and 10 MeV and beyond. Okay? So these are very, very energetic particles, or very energetic bursts of particles. The lightning leaders, okay, from the video I showed. Here is a leader tip, okay, and the high fields here accelerate electrons, which then collide with air molecules and bremsstrahlung off photons. If that lightning happens to be occurring, the leaders happen to be traveling in an upward direction, okay, gamma rays will be released pointing upwards, and they can be detected by satellites in Earth's orbit. Okay. So, in the past year that the detector has been operating at full capacity, we've detected 3 events, okay, where we've got LMA activity in coincidence with a burst of surface detector triggers. Okay? In the interest of time, I'll only show you one of them. This is a more or less vertical column of lightning, but that's not a characteristic of all of the coincidences we see. But here's the map of what's happening in the telescope array surface detector, okay, immediately below that. Okay, this is the activity in one of, I think it was 4 surface detector triggers that occurred in close time coincidence with that strike. Okay, and here I've plotted altitude versus time. Okay, the top scale, this is 0.3 of a second. This is about 10 milliseconds on the bottom scale. Okay, and what we see is the dashed lines are the telescope array surface detector times. Okay, and these all are confined to the initial breakdown phase. Okay, the leader phase of the lightning formation. Okay. Now, after we found those events, we went back and looked at some of the data from the period when we didn't have a fully functional detector. And we had deployed what are known as slow antennas. These slow antennas, operated sporadically, but we did find one coincidence of a TA surface detector trigger burst with some slow antenna activity. Okay, so a slow antenna, this looks like, and I'm pretty sure it is, a aluminum salad bowl with another aluminum plate in the bottom. So this is just a big capacitor, and this is read out with a RC time constant of about 4 seconds. Okay, and this is just a picture of my student and postdoc refurbishing one of these detectors a couple weeks ago. So what do we learn from the slow antenna data? On September 2014, seems like September is a good month for lightning in Delta, it turns out. This is in blue is what we read out in the slow antenna data. So you can see the steps in the electric field, okay, that arise from the atmospheric breakdown. The dashed lines are the TASD trigger times, and the dots are National Lightning Detection Network cloud-to-ground strikes. Okay, so you can see that these line up with little blips in the electric field. Now, what exactly do we expect in this in the leader model of lightning breakdown for this slow antenna? So now I've zoomed in on just the first step in this process, And what we see is typical of a leader return stroke field pattern. Okay, we've got a constant field. During the slow-moving leaders, we have a more gradual change in the field. Okay, then with the return stroke, a very abrupt change in the field. Okay, and this is typical. You can look in your Lightning 101 textbook and read all about this. Okay, superimpose that with the times of the surface detector triggers that we saw. Okay, 2 of them arriving during the leader phase. Okay, and then here is the NLDN, the National Lightning Detection Network, recording the ground stroke. In addition to the LMA information we got, this is equally exciting, a slow antenna measurement of the which clearly correlates the what we're seeing in the surface detectors with the lightning leader stage, okay, which is responsible for the terrestrial gamma flashes. Say the model at of the
Just the leader, but without it falling up on the cloudy ground.
you can have that. You can have that. This is one event that, in my mind, it was lucky that we got it at all. But yeah, this is kind of we were lucky to get kind of the classic picture here.
I used to lead wilderness trips, and a kid I was supervising, I think, got caught in a leader of lightning, and all his hair went. All his hair and his arms flew up, but there was never a lightning strike.
Not all leaders are followed by a cloud to ground strike. Yeah, that's true. Fortunately, so unfortunately, what we don't have is simultaneously surface detector and LMA and slow antenna information. But the picture seems pretty clear that what we're seeing is downward directed. What? But it is September, so we're crossing our fingers that this is going to be a good month for us. And so I'm going on an hour here. So all the particle physicists in the room didn't jump up and howl, wait a minute, you're saying these leaders are kilometers in the air. How can you be seeing gamma rays at the ground? Gammas don't travel that far. In fact, that's true. The interaction length is only about 300 meters at maximum. Okay, but the models that predict terrestrial gamma flashes observed from space say that I can have up to 10 to the 19th photons produced. Okay, so not many of them have to be able to travel a kilometer to give us a signal. Okay, in any case, I've been working with a undergraduate, Ryan Levon, on doing J-ONT simulations of the atmosphere. Okay, and indeed, using kind of a pretty standard gamma flash model that we found from somebody's PhD thesis, we're able to do a reasonable job of predicting about 10 to the 4 minimum ionizing particles, for a surface detector that's kind of right in the path of one of these flashes. Okay.
So the leader really does 10,000 joules of energy in just a photon.
Just in the yeah. This is a lot of coulombs, tens of coulombs of charge are exchanged. Okay, so in summary, since August 2015, we've been this detector's been in full operation, and we've recorded multiple events in time with trigger bursts, in which trigger bursts are in time with LMA or slow antenna activity. Everything we see and measure and calculate tells us these are consistent with downward TGFs arising from negative leaders. This is an exciting development, and we're preparing a paper to be submitted shortly. Okay, so this is my conclusion. And anticipating the questions, and maybe I should get one more hit of sugar here. I've talked about how I think energy spectrum and anisotropy studies are going to be enhanced by the statistics available to T8 times 4, and we should be optimistic that we're going to learn some interesting things in the next 10 years. We will be making improvements to cross-section measurements, but I think there's some other challenges that need to be worked out as well before we can really understand composition challenges to the modelers and to the measurements that one can do at the LHC. The Tara experiment is set and is in the process of publishing the first limits on the radar cross-section of air showers. And exciting news, we've begun to study what appears to be terrestrial gamma flashes, downward directing terrestrial gamma flashes in coincidence with the surface detector at the telescope array. Thank you.
It's disappointing that the radar doesn't give you what you want, but there's something there because there's a lot of electrons. There's radar photons bouncing off of those electrons. Whether you don't get the spectrum you like.
Well, it's a signal to noise question. It's a signal to noise question. Absolutely, electrons have to be scattering the RF, but are we above this galactic threshold or below? And with what is really a pretty souped up detector, I mean, the electric bill of our 40 kilowatt receivers was, or our 40 kilowatt transmitters was $6,000 a month. I mean, this is going all out. We're not above the threshold.
But if they're not actually flowing, they're actually bouncing around. Then you're not going to.
Well, the chirp is coming from the fact that you've got a wave front that's moving with respect. It's not the actual moving electrons. It's the wave front of electrons moving that is giving you a superposition that's resulting in this frequency shift.
Yeah, I have a question. Getting to the GZK cutoff, can you tell us physically why there should be a GZK cutoff? In other words, what led the people to predict such a thing?
What led to the prediction was the observation that there's a cosmic microwave background.
Yeah.
Okay, and people who know high energy physics know that there's a phenomenon known as photoproduction, where you can produce pions. Somewhere I've got the Feynman diagram here, where you can produce pions by the decay of a resonance that gets produced when you smash the photons together with the hadrons. So this is a kind of a discrete mechanism by which energy is lost that turns on when the protons have enough energy that in the center of mass you exceed the energy of that particular resonance.
Microwave photons.
The microwave photons act like, they start to look like hard gamma rays that your proton is colliding with. And when the center of mass energy is high enough, you can produce this resonance. That resonance is going to radiate off a pion, and you lose that energy.
But you're assuming then that this is the only source of high energy to begin with. That when you lose that, then you lose the energy. I mean, you lose the statistics at higher energies. And so, I guess my question is there any evidence for any other processes?
Is there any evidence for any other processes? So the angle process can be explained by a similar mechanism, okay, which is that these microwave photons interact with the field of a proton or a heavier nucleus, okay, and pair produce an E plus E minus pair. Okay, energy gets lost through that E plus E minus pair. Okay, that happens at a little lower energy than the GZK cutoff. Okay, but models of propagation of cosmic rays through large intergalactic distances, accurately simulate that shape due to this effect.
So you mentioned several times in this lightning studies, some national network which measures times of strikes.
Right.
How do they detect? I mean, how is it detected?
That's a very low frequency network. I want to say like 100 kilohertz to megahertz type frequencies. But they're they're looking for very low frequency emanations from lightning. At that frequency, they can travel. They can follow the curvature of the Earth. Okay, so you can detect from quite far away lightning strikes. As a result, the spatial resolution and the time resolution is not as good as it is with a local LMA at higher frequencies. But nonetheless, every cloud to ground lightning strike in the United States now is recorded by one of these, and probably most advanced countries as well now record these.
So how do they get actually spatial resolution? If that signal is bouncing from ionosphere or is, then
from timing information.
And so there is a network of stations?
There is a network of stations around the United States on mountaintops and not nearly as close spaced as the LMA array. I'm not exactly sure what the spacing is, but it's enough, and the wavelengths are enough that they're able to pretty reliably record cloud to ground strikes. Somewhat inefficient for cloud to cloud strikes. Okay, so it's kind of a matter of how much current is there in the strike, what the efficiency is going to be.
Current is bigger in cloud to ground?
Current tends to be bigger in cloud to ground.
Carl?
So, did I understand you to say that with the lightning strikes, that what you're measuring in the surface detectors are the gamma rays that are produced by lightning?
Well,
And not, so we have lightning.
it starts out as gamma rays. Okay, very few gamma rays are going to travel several kilometers unscathed. Okay, rather they are going to Compton scatter off of electrons, which are then going to Bremster along other photons. So there's probably some electromagnetic process that goes on, starting with a gamma burst and ending with some electrons and photons on the ground. This is what we finally detect.
But you're not seeing cases where the cosmic ray actually produces the ion channel for the lightning.
We have not seen one of those yet. That would be, I'd be talking to the New York Times instead of you guys if we had that. Yeah.
What does your salad bowl actually measure?
It's measuring the electric field at the ground.
Okay, just
It's measuring the electric field at the ground. Okay, as you might imagine, the electric field at the ground climbs when lightning's getting ready to strike. In fact, people like to attach wires to rockets, and when the electric field on the ground gets high enough, shoot the rockets up into the air and watch the lightning come down the this is a real area of study. People really do this. So.
What sizes of fields are you talking about? And how big is the change?
Why is my disconnected? Oh, I've lost my. The plots I've shown are on a relative scale. I could guess a number, but I'd be guessing, and rather than do that, let me say I'm not exactly sure what magnitude fields we're talking about. I mean, we've got a coulomb of charge, a parallel plate capacitor with a coulomb of charge. That's 1 kilometer separation. Everybody who's in physics 2220 now, work that out.
Volts per centimeter or something like that? Is that the standard? I mean, we're just sitting there in an electric field, right?
So 30,000 volts per centimeter is spontaneous breakdown, of course, when you rub your feet on the carpet. I know that the fields present in clouds are about an order of magnitude less than that, about 3 kilovolts per centimeter. Now on the ground, they're going to be somewhat less. I mean, depending on how big of an area the charge on the ground is spread out. Good question. Sorry, I don't have a quick answer.
We're positively charged and the atmosphere is negatively charged, or is it the other way around?
So by and large, the ground is positively charged, and I guess I'll have to give a lightning colloquium sometime. So the ground is positively charged. Clouds tend to be negative charge down here and positive charge up here. That tends to be what it's like. The reason that negative cloud-to-ground lightning is the most common is because that's the most straightforward path. So that's about 90% of lightning. About 10% of lightning is going to be when this positive charge region discharges to ground like that. These tend to be much higher current events. They also make for prettier pictures because they tend to come at the edge of a storm system where you got clear sky over here and a cloud over there, so you get rainbows in the background and stuff.
So if that hotspot and Anisotropy turns out to be a real thing, what do you hope to learn? It looks like it's still a broad area of the sky.
Well, what are the sources? People have been saying that active galactic nuclei are what's responsible for the sources. Is there a candidate, active galactic nucleus in that source? It's still a tricky business because there's a lot of magnetic fields between us and the sources, and the 25-degree smearing might be just a result of how much curvature we're getting from the magnetic fields, and so that might be kind of a fundamental limit to how well we can ultimately do. But did you have a question, Wayne?
What are you doing to assure that the signal on the telescope array surface detectors is due to particles going through a scintillator and not just some electronic pickup?
Because you can look at the waveforms and see that they're charged particles, and it's not some bipolar ringing. Yeah, it's particles.
fire, an isotropic source of cosmic rays outside the galaxy, and then factor in galactic magnetic field, solar magnetic field, Earth magnetic field, would you then expect anisotropy?
Outside the galaxy, or
Isotropic from outside the galaxy, what would we see?
um,
Due to the galactic field.
Yeah, or whatever the drivers are.
I mean, I guess at some level you would see effects of poles in the field, but largely isotropic. If you started with an isotropic, if there are sources of high energy protons in the magnetic field, and let's see, Gordon unfortunately left, but he was doing a calculation on this. If these high energy particles are coming from in the Milky Way galaxy, these sources would be very unambiguous. It would be very clear that they were coming from localized sources in the galaxy, if that's in fact where they were coming from, even with the galactic magnetic fields, taking that into account.
So I just want to say, I don't think I've heard in the years that I've been hearing about TA, where you actually now are not statistics limited in some regard. So to me, that's like a huge, that's really, for me, I'm not sure if I've heard that before. It's always been sort of the statistics limit, which to me just is a testament to how much, it's a pretty amazing accomplishment that you've beat down statistical noise with all these measurements over the years. And I wonder, now that you have a systematic limit in terms of the composition determination, really what do you need to do experimentally to understand that better and beat that down? I mean, is this better Monte Carlo models of the detector? What is the limit there?
Well, I think we take data that's collected at the LHC or at Fermilab that tells us, what is the proton-proton cross-section? What is the, fraction of time that I get charged particles or neutral particles, produced in a collision of two protons. And so I take that and I have to extrapolate from what's kind of 10 to the 17th in our units to 10 to the 19th in our units, okay? And a model that works very good down here, there's a large lever arm for error at the higher energy end.
What about, you also mentioned an experimental
systematic.
Well,
it's okay. So it's I guess even if you had a perfect model, whatever that is, it still is going to rely at lower energy on lower energy inputs that you're then extrapolating. So what you're asking about is how do we reduce the 15 to 20 gram experimental uncertainty, and we've got teams of people and spending lots of time trying to figure that exactly out. You have to worry about things like the atmosphere. You have to worry about what are the daily and the seasonal fluctuations in the density of the atmosphere affect your measurements at this level, and the ability to measure those. And we rely on twice daily radiosondes that are taken at local airports. Do we maybe need to start flying our own radiosondes every hour to but getting into minutia of how how these mirrors, or the fluorescence detector mirrors, are pointed at the sky. The geometry, is a systematic uncertainty, right? If I'm pointing there, or if I'm off by a degree, right? I take that degree and I multiply it by a few kilometers, and I got a reasonable number of grams per centimeter squared that my X-max has moved by. Okay, so fine-tune my knowledge of where my mirrors are pointing. I'm no doubt not thinking of everything, but but these are the kind of minutia that if we're going to get that down much below where it is, we're going to have to do.
I think maybe we've kept John here long enough.